for the final morning lecture of the week. We will have Mr. Dr. Professor Andrew Jackura tell us about, I think, in my opinion, one of the most fascinating parts of field theory, which is the two-particle scattering in a finite volume. So please take it away.
Thanks. All right. So we've argued, looking at these finite volume corrections and trying our best to link up all these different techniques, from lattice field theory, effective field theories, and scattering, to try to understand nuclear and hadron dynamics from first principles. So part of that is correcting for the volume dependence, and we found last time that stable particles scale exponentially suppressed in terms of the mass times the volume of the object. I call it the length of the box. I'm going to call it the volume because length of the box is too long to say. So if you make this sufficiently large with whatever parameters you're choosing to do your study, these effects should be negligible. And that's what I will assume throughout the remainder of this lecture. Then we started discussing two free particles. In order to think about two-point correlation functions, I constructed a local operator to create two particles at the origin and then annihilate two particles at some spacetime x. Upon the Fourier transformation, I wrote down this generalized Feynman diagram where I have whatever the creation bit is, two particles propagating with total momentum p, so one has k, one has p minus k, and they annihilate at a. If this were a physical, like a truly physical process, this diagram would be zero because this is a vacuum-to-vacuum transition. But here I'm thinking about it as an analytic function and the momentum squared, so that we can start building this thing up to look at how the finite volume corrections scale. And then as we start iterating this with interactions, we can isolate a physical quantity from this object. So in terms of equations, this thing is written down here. I have a symmetry factor if the particles are identical, which I'm assuming here, so this is a 1/2 finite volume sum, integral over the temporal bit, so the energy. I have my Fourier transform with the coefficients, and I have two propagators. Here, these m's are the physical mass. I'm going to drop phys or infinity because it's going to get annoying. So why am I using the physical mass? Because I've already proven that they scale, that if this was the finite volume Feynman diagrams, that the difference is exponentially small. And throughout, I'm going to ignore this exponentially small correction. So these are the physical masses. So now our goal today is to look at, let me emphasize, this is free. Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah. That's, yeah. Yeah, I mean, this is the scaling, right? So depending on what type of precision you're after, those effects may be important. I'm going to assume, since I'm after scattering effects, and I'm not as ambitious as Andre in trying to get percent level physics, I'm trying to get a qualitative understanding of extracting hadron reactions from QCD. So I will accept that there's going to be maybe not, zero contribution to it, but negligible compared to the stuff I'm after. Okay, so yeah, so those corrections are there, but I'm going to neglect them for my purposes. And if you're more ambitious, include them. Your formulae get a lot more complicated. Okay, so now I want to find the finite volume correction to this propagator here, or to this two-point correlation function. So I need to take the difference of the finite volume version and the infinite volume version. The infinite volume, I just replace that sum with the integral. That's all I have to do. Again, I will assume some UV regulator for some intermediate calculations if needed. I won't specify it because, again, I argued that the finite volume correction strictly is independent of the regulator. And I'm going to assume and this is part of my assumption when I made my local operators, that these A functions are sufficiently smooth. And by smooth, I mean they don't have any abrupt changes as an analytic function of the momenta, so there's no singular behavior. It's sufficiently smooth. These are reasonable assumptions. Okay? So delta CL free of momentum. It's a symmetry factor, which I'll keep writing as a symmetry factor instead of 1/2, just so we can track where it is in case you don't want to deal with identical particles. Epsilon P minus K. Just rewriting it from over there. All right, so let's do the temporal integral. It's got 4 poles, right? So if I break this square up and this square up into 2 separate terms, I have 4 poles, 2 from here, 2 from here. So let me write down where they're at. I'll skip a couple steps in the intermediate because this is the last lecture, and I'm going to provide my notes to you so you can see some of the details in between. So don't fret if you don't know how I go from A to D. B and C will be in here, or there'll be an exercise to you. So the poles are at K0 equals omega K minus I epsilon. K0 equals minus omega K plus I epsilon. These two come from the first term. And then I have, which I'll write as K0 equals E minus omega pk plus I epsilon, and K0 equals E plus omega pk minus I epsilon, where omega k is the square root of m squared plus the magnitude of the momentum squared for k, and omega pk equals the square root of m squared plus the magnitude of the momentum p minus k squared. So in terms of the complex k-naught plane, we'll look roughly like this. So if I call this 1, 2, 3, 4, and this is 1, 2, 3, and 4. So I'm integrating along the real axis choosing the contour to close from below, using the residue theorem, we can pick up 2 of the poles. We'll pick up 1 and 4. So then we will substitute those poles once we cancel them out from the residue theorem inside here. And we find that delta CL use my shorthand notation I introduced. Let me write them both here. you should find this. All right, so note here, these A functions, if I think about them in like a Feynman-esque rule, right, this would be something like this. So before, they're a function of the four momentum P and K, but by doing this contour integral, I've effectively placed one of the particles on its mass shell. So here I'm choosing the K, the particle with momentum K, to have its temporal component fixed by the mass shell condition. So I'm going to write that explicitly as omega K with the vector K. And then the other particle still has a 4 momentum P minus K, but the temporal bit of K is fixed. Right? So effectively, if I draw it over here, A omega K, K, P, so this leg, it's on mass shell. Since omega K depends on the magnitude vector, it's kind of redundant, so I'll start dropping that. But note, even though I'll start dropping that, you know, we may think the other particle has momentum P. That's just because this notation's not great, but I'm trying to be compact. The other particle has momentum P minus K. Right. So let's think about this for a second. The other singularity can come from, or like the singularities of this finite volume correction to the free particle, or free two-particle correlator here. So here we see this denominator, there's a chance where this thing can blow up, all right? We saw before that if the integrand or the summand is smooth, then we can argue these exponentially suppressed corrections in the volume, but if it's a singular function, that's not necessarily true, and in fact it's not true. And let's think about when this denominator can blow up, and if we think about that loop, the possibility that two particles propagate freely, so both particles are on their mass shell. So if E star, which is the square root of the 4 momentum squared, is greater than or equal to twice the mass of the particles, then both particles are essentially free propagating particles. So can this happen in this denominator? Well, let's break up this denominator into 2 terms. So you can prove that to yourself just by breaking it up. And if you think about possibly when this two-particle propagator can go on shell, which we said is this, if you stare at this long enough, we're going to work through some examples of different momenta. You'll find here that, say for example, if the momentum is 0, with the total momentum being 0, then this will be E minus M plus M. Well, this is going to be, the pole is going to occur when E equals 0, which is going to be less than our twice mass condition. So, and you can extend that further. This term here is going to be regular or smooth within this kinematic region. So therefore, using similar arguments that we did for the single particle case, this thing will be some exponentially suppressed correction. and I'm going to ignore these terms. This term, however, when k is 0 and the total momentum is 0, this is E minus 2m. That's exactly the threshold condition. So as the momentum increases, this is just the total energy of the two-particle system. So this can be singular when the particles are real. So we cannot use the Poisson summation formula in the way we did before for stable particles because of the singular behavior. So then, delta CL free will be something like this. Okay, the last thing I'm going to do is I want to place these coefficients on their mass shell so I can remove them from the integral. All right, because if I could make this not depend anymore on, because these are some dynamic quantities I don't really have an understanding of, I want to try to remove all dynamics and see what kinematic effects are left over. And I want to kind of get rid of the momentum dependence. So, or at least as much of the momentum dependence as I can. So on shell, if I think about the center of momentum frame, momentum, which I'll use the star symbol as Sebastian's used, so the total momentum of the system is going to be this relative momentum that Sebastian's introduced, which is 1/2 square root of s minus 4m squared. And then the angular dependence, which the angular dependence is never fixed from an on-shell condition, right? So this is still remaining. What I can do to try to remove the dynamical quantities is I can let, if I think about my variables in terms of the center of momentum frame instead, which I would do for a reason, because I could define angular momentum that way, is I can write this quantity like so. So here, this again represents this situation, and I'm writing it by fixing the magnitude of the momentum. That's going to fix both particles to be physical particles. So I'm doing that. This difference here, if I Taylor expand, and I'll leave you to it, is going to go like K star minus Q star. This is the same condition, leave it for an exercise, and I say some more in my notes. But this is the condition when two particles are physically propagating, which is related to this case here, which is the energy when two particles are propagating. So they're both going to generate the same type of behavior. One's going to be in the numerator, one's going to be in the denominator. So the singular behavior here is going to be canceled by the singular behavior of this term. So the corrections from this guy are going to be exponentially suppressed. So I'm left with just the on-shell guy. And then, now that I've defined this quantity, I can use the fact that in the center of momentum frame of two particles back to back, I can define angular momentum. So A of Q star And the orientation is equal to the square root of 4 pi, convention I'm choosing. So now this function's in orbital angular momentum space. We have YLM's spherical harmonics. Now the spherical harmonics introduce an artificial singularity when the momentum is 0. So to regulate that, we're going to introduce barrier factors, which if you have any experience with scattering, you introduce these to regulate the dependence of the amplitude near threshold. So I'll introduce this. So at threshold, or so this is going to regulate the 1/k dependence here, and then it's just fixed to where when k is equal to q, there's no barrier factor anymore. So on the on-shell point, it's not present. So combining this, where I'm going to replace these coefficients by just this term here, because these extra terms are going to be exponentially suppressed, and then expanding in partial waves, I'm going to arrive at the result here that I want. And I'll write it like this. Delta CL is going to be sum in angular momentum. I'm going to do it for both sides. I have this matrix. I'm going to write out what this matrix is in a second. So here I have a matrix in angular momentum space, this F function. It is an entirely kinematic function characterizing the distortions from the finite volume. And if you've heard of the Lucier zeta function, this object is closely related to it, so much so that sometimes this is also called the Lucier zeta function, even though it's not written in the kind of usual way. And then we have our pole. Okay. So our finite volume correction in angular momentum space, so in infinite dimensional space, you have the two coefficients which characterize the dynamics of this, of the interpolating operator creating our two particle states, with this matrix F, which depends on the volume, and it's entirely in terms of kinematic variables, right? So in the infinite volume limit, as L goes to infinity, you can show that this correction here is going to go to 0. So what I said, well, it's going to go to 0 up to the integral of the two-point function, you may know, gives rise to an imaginary part from the branch cut, or gives rise to an imaginary part when the two particles can propagate. So it's up to that term, which for this thing is going to be unphysical, so it will never come on. But as far as the finite volume bit, that's going to completely get rid of the the correction goes to 0 as L goes to infinity. What I want to say, just escaped my mind. Yeah. So what we said here, so CL, and again, this is the free, but in general, CL equals C infinity plus delta CL. So this thing has poles, this thing has cuts, this thing has to know about both. And indeed, it knows about the poles, and then the integral term is going to know about the cut structure here. So this thing has both here. So this finite volume function, this finite volume correction function, plays a big role in the Lucier condition because it's characterizing the distortions from the finite volume. It's entirely kinematic. What we should see here is that the spectrum, if you wanted to look at spectral analysis of the correlator in the same way we did in the first lecture, you can isolate the poles here. This thing won't have the poles, and this thing will have the poles, and here they are. So everything seems consistent, hopefully. So I will often, so I'm now going to switch to now turning on interactions, and I'm going to do most of that diagrammatically. So I'm going to define I'm going to define this object here, let's say some coefficients A and B. Okay. So whatever these coefficients are, as long as they're smooth, non-singular functions of the momenta, I can write it as A times this finite volume correction term times B in matrix notation, and this is equal to the difference between these two loops, up to, which I'll write in yellow, all these terms I've been neglecting. So now when we turn on interactions, you're going to have two particles propagate along and then come together in some short distance kernel function. And if you're somewhat familiar with quantum field theory, you can write out a set of Dyson-Schwinger equations or Bethe-Salpeter equations or whatever name you use for them to describe such a scattering process. In the finite volume, you can do the same thing. So two interacting particles you can imagine I can write this term again, which is the free bit, and I can write this where, what symbol do I use? B. I'll define what B is in a second. All right. So this B here is a two-particle irreducible kernel, which is often called the Bethe-Salpeter kernel, as it is the driving term when looking at the Bethe-Salpeter equations for the scattering of two particles. So examples of two-particle irreducible for phi-4 theory, which is the example I've been dealing with. So if I think about perturbation theory of the beta salpeter kernel, you have the leading order contact term. This is two-particle irreducible. You have the T and U channel contributions, but not the S, because the S is going to be part of this object here, right? So I have the contact term, and this is the S channel diagram. So I'm only keeping two-particle irreducible diagrams, which won't go on mass shell in the in our energy region. So maybe I should call these B sub L's. Since they can't go on mass shell, and we're going to restrict our energy window so in the center of momentum frame, energy squared, or S, we have 2m quantity squared. There's a branch cut from scattering that we know about. Perhaps there's a 4m squared in phi-4 theory. It's like 4m quantity squared. I'm going to restrict my energy of interest to here. So I want to try to access the two-particle scattering amplitude. I will not be so ambitious to try to access 2 particles to 4 particles, or so on and so forth, nor right now trying to access to the left-hand cut that Sebastian discussed. I want to keep things simple and try to just understand the basic two-particle scattering amplitude. So if I do so, the two-particle irreducible objects won't go on their mass shell. And again, I use without proof, just based on what we learned before. That the beta saltpeter kernel in the finite volume will be the infinite volume one plus exponentially suppressed corrections. So then CLP will be this plus B now, not B sub L, plus all the other terms. If I think about what I'm connecting to here, the 2-to-2 scattering amplitude in field theory, which I've already said in words, is described by a self-consistent integral equation so here's infinite volume loop. So I will use the notation I of m to mean the two-particle scattering amplitude. And it's given by this self-consistent equation, which you can write the integrals out for. But you can also expand in the Fredholm series it's an infinite number of terms, right? So like in perturbation theory, this is what you do, but you can have a non-perturbative definition in terms of these in terms of the self-consistent equation, and to relate one to the other, you just sum it up, and then if it's if the coupling is large, you analytically continue, sum them up, and then go back to where you need to go. So the same idea as geometric series. So here I have finite volume loops in the beta saltpeter kernels. This is telling me that there's some way to access this two-particle scattering amplitude if I play the same game of relating loops to, or finite volume loops to infinite volume loops, and then resum the series. So that's what we're going to do. Again, I'm going to do this diagrammatically, and I'll kind of illustrate the first few terms. And you can construct a more kind of systematic way to do this if you just kind of sit down and kind of organize diagrams by diagrams how it goes. I have a little bit of that in my well, I have a lot more of that in my notes, but if you aren't familiar with it for the first time, it can be a little confusing, so I'll just illustrate it for a couple terms in the expansion. Okay. So then this 2-point correlator, which we know from L to Z can give us the scattering amplitude. We're seeing that in this diagrammatic expansion. So let me think about, we can also think C infinity, so the infinite volume correlator. So the infinite volume correlator, all I need to do is just wrap these legs up with the local functions that I use to create them, and you can sum up that series and you get the kind of scattering amplitude inside of here. What's the off-shell scattering amplitude until you place the legs on mass shell? Then it's the on-shell scattering amplitude. And this has the same structure that you see in field theory, where you have the disconnected pieces and the connected pieces. So let me do it over here. Well, let me start here. So let's start with the first term in the series. V, well, I can rewrite this thing as the infinite volume. Well, I'm not going to write infinite just to save time, plus our correction term that I defined over there. All right, so let me call this kind of C naught, all right, so C naught, C1. C1 of P is going to be too long to keep in that space. So CL1 of P all right, so these functions here are smooth functions in this energy region, as is the beta saltpeter kernel, by assumption of where we restrict our energy region of interest. So I can take this first term here and rewrite it as C, or as the infinite volume loop plus a finite volume correction. So that's taking this first term here, replacing finite volume by an infinite volume, plus the correction term. I can do the same thing on the right-hand side. Yes, I'll do it that way. Right, so I have 4 terms when I use this identity of replacing the 2-particle loop with the infinite volume plus the correction. We get the C1 term from here, so we're already reconstructing the infinite volume 2-point correlation function. But then we get extra terms, right? So we get one with an infinite volume loop here, but a finite volume correction here, infinite volume loop here, finite volume loop here, and then 2 finite volume corrections. So you can do this ad infinitum, and what you'll find is that you're going to recover from replacing all of the loops by their infinite volume counterparts is just the infinite volume correlator. So that's good, but then you get all these extra terms. And the way that they're going to be organized is, let me write this. So fine after repeated applications, so you find that finite volume loop or finite volume correlator is the infinite volume correlator plus how do I write this? Oh. Sorry, using the wrong symbol. So I'm confused. Right. So stare at that for a second. Let me erase this over here to kind of write down what the expression looks like. So what you get is the sum of the infinite volume loops with the beta saltpeter kernels are going to give you the scattering amplitude. So that's the shaded object I wrote. But then the end caps, so the two vacuum vertices to two particles, they're also getting dressed as well. And you can kind of see that you can see that in this term here. So here you get the kind of our original vertices, but then in terms like this, you're going to get a finite volume correction similar to this, but now the right-hand side has been dressed by one insertion of the beta saltpeter kernel. So that's going to keep happening, and then you're going to end up with the scattering amplitude that's dressing it. In fact, it's no dot, dot, dot. That is just the scattering amplitude. Sorry. There we go. So this would be kind of like an off-shell vacuum to two particle Dyson-Schwinger or beta saltpeter equation. Of course, on shell you can't have vacuum go to two particles, so these are just the constructs that arise from our interpolating from the vacuum to the two particles. And then in between them, and you can see that starting here, or I should say, hang on, am I missing a term? I'm missing a term, sorry. So let me rewrite that. So I'm missing this. Knew something looked a little wrong. All right. So here then, you're going to have first the finite volume correction coming from this term here and it being dressed. And then, so you can see that here and here. But then you're going to have cases where you have finite volume corrections that are sandwiching a beta saltpeter kernel. And as you keep playing this game, this is going to expand in the middle with repeated beta saltpeter kernels to give you the scattering amplitude. And that will happen over and over and over again. And again, you can come up with like an iterative way to do this. So what you find, I'm going to define I, A, bar, just because I'm unimaginative, as the dressing of the creation and annihilation coefficients. So then delta CL of P is equal to IA I'm not connecting well, I should, yeah, let me do it that way. That'll be easier on me. Which I will define as maybe a box. So this thing will have a box. All right, so that's the first term in of the three brackets. That's the first term in the box plus the second term plus the third term, and so on and so forth. So each insertion of the scattering amplitude is accompanied by two finite volume corrections on either side. So if I write this out in terms of the matrix notation I introduced, so this is something like I, A bar, dotted into, not I, sorry, F plus IF dot IM dot IF plus IF dot IM dot IF dot IM dot IF plus so on and so forth, up with A bar star. So in here implicitly, Sebastian covered partial wave expansions of the amplitude. So I have the amplitude here. I can also partial wave expand that as well into angular momentum space. So that's what I've done here. So these are matrices in angular momentum space. Now, angular momentum is not a good conserved quantity as it is in the infinite volume for finite volume, because finite volume breaks up rotational symmetry, but we can still label things by the angular momentum eigenstates, just not enforcing the conservation of them. And then what you need to do in practice is relate the angular momentum eigenstates to eigenstates of finite volume group elements. So it's just the discrete rotations for different symmetry actions. I won't discuss that here. If you read any lattice papers that discuss hadron spectroscopy, they give references and details of how to do so. And if you're interested, I can send you more information. But that's not the purposes here. Here it's just trying to construct how this relationship works. So now I see a geometric series. And us physicists like geometric series because it's one of the few we can do in our heads most of the time. Nothing. All right, so if I have sum of n, xn, 0 to infinity, 1 plus x squared, so on and so forth, which is 1 or 1 minus x. And I know I just made a little joke, but please check to make sure I wrote that correctly, because there's a very real chance I didn't. So if x is less than 1, you can do this summation and get this exactly, but by analytic continuation, I can always, this is my analytically continued form. And that's exactly what I have here, all right? So what I'm going to do is pull out one factor of IF. Right? These factors of I are accompanying me in the same way as Feynman diagrams. So see delta CL of P is equal to I, A bar, IF times 1 plus I, M, I, F, so on and so forth, I, A bar. This is I, A bar, I, F. The sum goes from n equals 1 to 0, and this isn't this infinite dimensional matrix sense, so all the usual mathematicians weep if we don't do it correctly, but this is what it is. I, M, I, F, N. And I'm forgetting something, I, A bar, that should be start. So if you sum that series, we get I, A bar, I, F times 1 over 1. 2 factors of I is a minus sign, but this is also a minus sign. So that's plus M, F, I, A bar. And this is the finite volume correction, right? So now the finite volume correction knows about, these things are irrelevant for what we're after, but it knows about this finite volume function, which was giving us kind of the free two-particle interacting energy states. But now we have the scattering amplitude in there. So the free interacting energy eigenstates are going to start being shifted by the presence of the scattering amplitude. So how does that shift occur? Remember, the finite volume correlator knows about the poles of the discrete energy eigenstates, which are the things that we're calculating from lattice QCD. The infinite volume knows about the scattering amplitude. The finite volume correction knows about both. So where do the poles occur? Well, when this denominator vanishes, and in the context of matrices, 1 plus M, let me write arguments in here. So when this determinant vanishes. And this here is kind of a generic form of the Lucier quantization condition. So this is valid for 2 scalar particles in any angular momentum state that we have. You'll see a bunch of different forms of this thing, but overall they always have the same structure where you are linking the scattering amplitude to the finite volume correction. And when the energy equals the energy of your discrete spectrum. So it only holds when the energy is equal to the energy of the spectrum. But you see this in many different ways. Sometimes you write this in terms of phase shifts. If you're doing low energy scattering, in principle, this is a determinant over an infinite dimensional angular momentum space. So it's like, okay, this is nice and formal, but now we can't make it practical. But we can make it practical because in terms of partial wave amplitudes, you have angular momentum barrier factor suppression. So the amplitude scale, like the momentum to the power L or 2L. So you can imagine if you're doing low energy scattering, only a small finite number of waves are going to contribute to the actual process of interest. And with good approximation, you can ignore the other contributions. Of course, higher in energy you go, the more and more you need. So you have some physical way to truncate this infinite dimensional determinant. That's nice. If you're doing really low energy scattering, which is some of the first papers that were looking at this, you can write this in terms of an S wave, which is the lowest angular momentum state, S wave phase shift relating to the Lucier zeta function, if you are familiar at all with that. If not, that's one that you see quite often in the literature. I can also kind of rewrite this. I'm pretty much finished where I want to get, but to make a point. So a lot of times you see these in different ways as well. Given the fact that F is only going to have poles at the free energies, if I'm interested in the interacting system, I don't care about these poles here, it's just the poles coming from here. Likewise, I can start moving, say, F outside this denominator as well, and it's not going to affect the quantization condition. The quantization condition always holds at the interacting two-particle spectrum. So I can write it like this as well, which is useful because then you can make arguments of, well, if I'm looking at really weakly interacting systems, so for example, so let's say the interactions turn off completely, well, this term won't be there, and I had the determinant of F, but that just gave me the free spectrum I had before when we did just a two-particle non-interacting correlator, so everything's consistent. And then if energies are low enough, I'll kind of write down what I said before. So if energy is sufficiently close to threshold, then M goes like ms, the S wave amplitude, or I'll identify just the S wave amplitude, which you can write in this non-relative, or in this relativistic normalization. So here's the symmetry factor, 1 over Q star cotangent delta minus IQ star. And for scattering near threshold, Q star cotangent delta at leading order is the scattering length plus higher order terms. So if S wave scattering is dominant, then you have something like M inverse plus F S equals 0. So just the S wave contributions. The scattering amplitude has an imaginary part coming from the two-particle phase space that you saw in the K matrix representation. So imaginary part of M inverse equals minus rho. I didn't say it explicitly, and that's my fault. F, the imaginary part of F, I think I said it in words, but I didn't write it down. The imaginary part of F, one can show, I say some more details in my notes wherever they are, and you'll see them online. Remember, we had the integral with the I epsilon business. Well, that's the integral of a two-particle loop. That gives you a phase space factor as well. So the imaginary part of F is equal to rho. The sum of these two terms is going to give you 0 imaginary part. So this is a condition that is required by the quantization condition because it's built upon isolating when two particles can go on their mass shell, which is the same principle that is used in constructing amplitudes that satisfy S matrix unitarity. So they build in the same principle. We should have that unitarity is satisfied for the quantization condition in this finite volume setup, and in fact, we do get that. So you see that in the simplest case, again, try it kind of offline after the school, of taking the explicit function, find the imaginary part. You'll see you get the phase space factor from these same phase space integrals that Sebastian showed, and it will come with an opposite sign from the imaginary part. So this allows you to relate the Q cotangent delta to some geometric function, the Lucia zeta function. And on your exam, you will do this example for weak coupling expansions and look at how the energy shift is from for some weak system. So take note of what I just did. All right, so I think I'm out of time. Thank you very much. I very much appreciated coming here and giving these lectures. And I've talked to quite a few of you. If I haven't talked to everyone, I apologize, but it seems like you guys got something from this. So I hope you can take away a lot of the modern tool sets we're using to try to answer how to get at few-body hadron nuclear physics from QCD. And there's all these tools we try to use in conjunction to learn something and make progress in different ways. So thank you very much.
Thank you, Andrew, who also was our master organizer. Do we have any questions for Andrew?
So what we calculate on the lattice is the energies. That's what we calculate on the lattice. We can compute these functions, they're known, so we compute them, store them, and we have the scattering amplitude here. So we can get access through the scattering amplitude indirectly by ensuring that this equation, and the way we do that in practice, because this is a complex function, we use scattering theory results, so writing this in terms of, say, a K matrix, to parameterize something easier, because the K matrix is easy to parameterize. It has to be real coefficients. So we parameterize the K matrix and fit those with this condition being the fit condition. Yeah, so we have some parameterization for the K matrix or the amplitude, plug in the energies we calculate from lattice QSD using the techniques Amy discussed, and then we just try to minimize this condition. So because lattice says you can't get amplitudes directly, we were persistent and found a way to do so. So now we can get at scattering reactions. And let me just say, here I did the simplest case for two scalar particles. This, so any two-particle system can be analyzed. Andre can talk to you about the work on two nucleon systems, which he's a big part of trying to pin down how to get at properties of, say, the deuteron from using these techniques. There's a whole slew of stuff going on in hadron spectroscopy, so mesons and baryons. Andre's done some work on that as well, where we try to answer spectral questions to get at using this method. This also has played a role in looking at electroweak decays of hadrons. So you can also say, well, what if I have an electroweak decay of a hadron and it goes to two particles? In principle, these are going to be finite volume effects. We've done that, or that in principle has been set up. Have you done any work in electroweak decays? Because I know, Stefan Meinl has done so. I mean, you have the G of A, but that's not the same idea.
No delta yet.
Yeah, no delta. Yeah, one day though. And the finite volume formalism has been extended to even answer more interesting reactions that aren't easily accessible from experiment. So Sebastian will talk about three-particle scattering in the colloquium this afternoon, and that's a big push that's happening there as well. Yeah, when you start getting into, so Sebastian will talk about using the three-body formalism to investigate the TCC, this tetraquark candidate, and they, I mean, I won't spoil the surprise. You see his talk. He'll talk about that study a little bit. That and it gets more involved, yes, but again, we're persistent.
One of the things I learned in training how to not be a jerk, as they say these days, is when you ask if there's any more questions, you're supposed to wait like at least 30 seconds for those people who need a little extra time to feel motivated to ask their questions. So any questions? And you get the awkward silence, but you have to live with it.
For deriving this or using it? Because deriving it, it's all right here, Yeah. Yeah, I mean, so it uses, it uses a lot of techniques from field theory that are knowledgeable, but then you have to kind of build in these other ideas from effective field theories or orders approaches. But, I mean, if you break it down step by step, just using properties of what on-shell physics says and separating out, well, it's short distance. Again, it's the same thing as Andre said. Short distance stuff, I don't care about in the sense that it's making up what's going on in the interactions that I'm trying to measure or determine. But the long-range physics I can actually control, because that's, in this case, two particles propagating, and that's stuff we measure. So it really involves just breaking down these complicated diagrams into something, straightforward. I have a bubble loop. We all attack this in field theory. In the finite volume, it's this kind of unknown thing, but I know what it is in the infinite volume, so I just judiciously add zeros and manipulate them. So it's not a lot of advanced concepts. It's more just using a few concepts over and over and over again to build this up.
Is this our final lecture?
Yes.
Ooh.
Yeah.
I can abuse having the microphone. I'll just repeat myself a little. There's no amount of reading will make up for sitting down and actually doing stuff. So you will never understand just by reading unless you're Weinberg or somebody like that, and we're all not Weinberg, so.
Yeah.
So make sure at some point you put down the reading and you actually calculate. That's where you're gonna learn.
Yeah. Yeah.
And the other thing I still firmly believe, for most of us, again, unless you're a Weinberg, for most of us, persistent hard work is what you really need to succeed. Like, no matter how, if you can be a genius, but if you're too lazy, you're not going to make it, right? And if you don't feel smart enough, you're like the rest of us, and you just have to work hard, and eventually you're going to get there.
Yeah, so let me kind of just a little more on both of those. So I try to present my notes and doing these calculations in somewhat detail in the way I think about it. So if you read some of the papers, there's no book that says how to do this because it's all kind of modern stuff being developed. But I'll try to link some research papers that have kind of the steps to how to do this, and it's more or less the same thing. So I presented you my flavor of it, and I do believe if you go through my notes and kind of actively, not just read them, but actively participate in working it out, you'll get the idea. I think you will. And you may have a better way to think about it, and, great. My original background is in scattering theory, much like how Sebastian was, so I kind of came into this and had to abruptly learn a bunch of this stuff as I kind of geared towards the connections between scattering and lattice QCD. So this is my understanding of it, and I try to present it in a way to not just talk to an audience, but I'm really talking to myself as I'm working through it. So that said, if you see typos in there, it's because I am working it for myself, so let me know, and I'll fix them. But yeah, you have to go through it. So I tried to help you by making it so where you can go through it and understand. But again, feel free to shoot me an email if you're interested in more of these details, some of the more kind of advanced techniques if you're not too familiar with them at this point. Everyone's
Maybe
hungry.
that's enough awkward silence.
Yeah.
All right. Okay, let's thank Andrew again. And of course, the organizers. Do you want to say anything?
So the only thing,